Welcome to Tone Academy. From last two sessions, you have actually seen we are dealing with atomic structure. I think in atomic structure, you will be having each subtopic, you will be linked to your pre-engineering test like NEET or whatever. So we were discussing first the dual nature of light in the first session, and I was actually basically telling you about Planck's quantum theory. Now, in the second session, I was actually going for the applications of Planck's quantum theory, which revolutionized physics or science. And then we have gone into the photoelectric effect, which I can call it to be one of the best applications of what the Planck's quantum theory. As I told you, there was a precedent always that whosoever is telling theory, it was actually bundled into and then sent to Einstein, and where he used to tell his own version of what people wanted to tell. So in that process, actually the entire Planck's quantum theory was told by Einstein in a simple way: radiation is just a shower of photons. Right? So the first two sessions we have gone in for the Planck's quantum theory, which revolutionized physics, which says that light has dual nature. It can be sometimes behaving as a wave, sometimes behaving as a particle. Similarly, we have photoelectric effect, and I told you 6 questions in the end of the session if you're following me. And I think in all the 6 at the end of the session, all the 6 questions are you can bank on, and you will be getting that in exam, right? And moving forward, and here is Roman number 3. Rather, each subtopic I put a Roman number and I draw the attention of everyone. Now, in Bohr's model, like in atomic structure, what exactly we are doing? If I can write the aim for this chapter, what exactly you're doing in atomic structure is basically it is like this. You know the aim of this chapter, if I can write, then I say to pinpoint, and I would like to underline what exactly you're doing in atomic structure, right? What is that you're doing is to pinpoint, in fact, the address of electron. So if someone is asking you what exactly you're doing in atomic structure, then you tell them that you are actually pinpointing the address of the electron, because we need to locate to the maximum, without any error, without any uncertainty. If you are able to locate the electron, and then I think you are successful, then you please understand that the aim of the chapter is basically to pinpoint address of the electron. You must understand. See, it is always surprising to me. It is always surprising, as we have, there is a regular arrangement outside the nucleus in an atom, and there is a regular arrangement inside the nucleus of an atom. So there is an regular arrangement. You are not throwing, if I give you 100 electrons, you are not throwing out in a random fashion outside the nucleus in an atom. You must understand there is a regular arrangement. When there is a regular arrangement, then I think there should be some schemes in which you must be distributing the electrons. There must be some schemes. There must be some rules and regulations in which you are actually placing these electrons, and where are they placed, what is the exact position of the electron. All these are actually discussed in atomic structure, you must understand. Finally, I can say we are actually giving an identity to the electron as you and me have identity, and people call by us names and we raise our hands and say hi. So please understand this. So let's slip on to the topic now. If someone is asking you what is the aim of atomic structure, what is that you are exactly doing in atomic structure, you are actually pinpointing the address of the electron. Now, what do you mean by this? For example, if you wanted to write a letter to your friend in Mumbai, how do you do that? And have a look here. Suppose if you wanted to write a letter to your friend in Mumbai, how do you write it? To Mr. X. To Mr. X. X is your friend in Mumbai. Then you write your door number. Then after writing the door number, you'll write the apartment name. I call it to be ABC building. Right? And the area name, if I can write it, I can write this to be Manish Park. The area where you need to get down. Right? And then you write the bigger area, that is the Andheri, and then you have Mumbai. Now, this is how we write the address when you write a letter to your friend. When you write a letter to your friend, this is what is the sequence you will follow. To Mr. X, door number, ABC building, Manish Park, Mumbai, Andheri. So what is happening here in the sequence, what is happening is, on moving from Mumbai to the door number, On moving from Mumbai, you got down at Mumbai, then you were taking an auto and go to what? The door number. From Mumbai to the door number, the probability of finding Mr. X increases. The probability of finding X increases. You must understand. The same sequence exactly is followed in atomic structure. Right? So initially, one fellow will suggest, if you ask me where is electron in an atom, then one fellow suggests shells. Shells. Shells, synonymously, I'm actually referring to Mumbai. Right? And then someone is suggesting subshells. Then you are actually going into Andheri. Right? And then someone suggests, orbitals. Then you are actually going into Manish Park. Then someone is going into door number, knocking the door and venturing into the apartment to check out where your friend is, and that's nothing but the Schrodinger's wave equation, where you actually pinpoint very much 99.999% probability of finding the electron. That is how the synonymous way to understand what exactly you're doing in atomic structure. So basically what we are doing in atomic structure, if someone is asking you, why do you read, what is the aim of this lesson, is basically to pinpoint the address of the electron, similar to what you write a letter to your friend. You must understand this, right? So let us start off with Mumbai, right? Mumbai, in the sense, we are looking at the Bohr's model of atom, Bohr's model of atom. Remember, there were earlier theories. There were earlier some theories, that the real challenge was the stability of the atom. How is atom stable? There was one fellow called Rutherford. He used to say the electrons are revolving round the nucleus, round the nucleus. Now the issue is, when you say that, it's almost like, planets revolving round the sun, right? So if you say that the electrons are revolving round the nucleus, and if I ask you to revolve around this room, after some time you'll vomit energy and fall down into the nucleus. So the very idea of the electrons revolving round the nucleus seems to be prima facie fine, but I think when you do that continuously, you're vomiting energy and finally you collapse down into the nucleus. So when you collapse down into the nucleus, the very stability of the atom is given a miss. Then what are we doing here? We should run away. So with the very stability of the atom at that point of time is a question, and then Bohr entered and he has done his all homework, and he will be basically explaining the stability of the atom. In spite of electrons revolving round the nucleus, how is that? How is that the atom is stable, and why the electrons are not falling into the nucleus and why the atom is not collapsing is the biggest challenge of what? Bohr. You must understand this, right? So these are all addressed in Bohr's model, and what I'm doing is, I give his postulates, his proposals in his own wordings, not the one which you get it in your textbook. The textbook postulates are basically the inferences that are given out from these statements given out by Bohr. So in the research paper, what exactly is Bohr telling to address pinpoint the address of the electron in this chapter? And I draw the attention of everyone now. Here is postulate number 1 for Bohr, and then I go for the inferences and I go for the equations, and then I link that to the exam. Watch carefully here. These are the proposals of Bohr. Watch carefully. Proposal 1. And he is so confident. He's basically so confident that he uses a singular word. Look into this proposal. In fact, this proposal number 1 has fetched him Nobel Prize. It has fetched him Nobel Prize, and this addresses the stability of the atom. Earlier, no one could do that. So I draw the attention. Here is proposal number 1, and see what he's telling. I propose. He's using the word I. He's so confident, man. He's so confident. He says that I propose. I propose. I propose. He is proposing NRPs. NRPs. And I would like to underline this. NRPs. Now, what exactly are NRPs? Now, understand this. These are nothing but non-radiating paths. These are non-radiating paths. This is a revolutionary statement, man. Please understand this. The very challenge which is actually hitting Bohr is basically to explain stability of the atom, which no one was able to do that. So in the process, in the guise of that, I think he's actually proposing non-radiating paths. Now, non-radiating paths for whom? For whom? For electrons. For electrons. And where are you proposing this? Where are you proposing this? These are around the nucleus. Around the nucleus. And where is this? In an atom. In an atom. So please understand his first proposal, which is so revolutionary. And when he was actually proposing, the room was full and all are learned persons, all scientists are sitting over there. And look at this statement, what he's quoting. I propose, he's so confident. He says, I propose non-radiating paths. That's non-radiating paths for whom? For whom? For electrons. Where? Around the nucleus. Where? Inside the atom. It's revolutionary for the simple reason, you just wanted to compare Bohr's theory with Rutherford's theory. He was actually telling that the electrons are revolving around paths around the nucleus. When you do that, you're constantly vomiting energy. Vomiting energy, after some time, what you do is you vomit the energy and collapse into the atom, and the atom itself collapses. That's what is the proposal. And look at this, exactly opposite, and he was very confident in what he's telling. He says that I propose NRPs. Now what's a non-radiating path? Non-radiating path is a path where, as long as, I draw the attention of the students. Look into this, let's understand this. An electron, as long as it is in the path, it's neither vomiting energy nor losing energy. Such a path is called non-radiating path. As it says, non-radiating. That means that I am not vomiting energy. I am not vomiting energy as long as I am in the path revolving around the nucleus. Neither I'll vomit energy nor take energy. That's what is called a non-radiating path. Non-radiating path. You must understand. Now, when you propose such a thing, it's hard to convince people. It's extremely hard to convince people, because when I move around something, I think I should be what? Vomiting energy. You must understand that. You must understand that, right? Now, if the moment he proposed this, there was almost like a rebellion among the learned people. What nonsense is this? It looks silly that, electrons around the nucleus, and you say, and you propose non-radiating paths. Non-radiating paths, that means that you are actually telling us that the light is not coming out of the atom. The light is not coming out of the atom at all. This is ridiculous, because you, me, everyone know, of course, that the light does come out of the atom, because the spectra is readily available to you. The spectrum is a reality. The spectrum is a reality. Light does come out from the atom. You need to tell that. Now, if you propose non-radiating paths for electrons around the nucleus, then you are basically telling that the atom is not radiating and the light is not coming out. And how do you explain spectra? And there was a great rebellion when he proposes, I propose non-radiating paths for electrons around the nucleus. There was a great rebellion, and people used to raise their hands and please tell me, man, how the light is not coming out of the atom? Because spectra is a reality. Spectra is a reality. Of course, discontinuous spectra given by atoms is a reality. How do you reconcile this? The basic question, the moment he proposed this, the first question what people asked is this, and I want to highlight this. In fact, the question which comes out when you propose non-radiating paths, the question that arises is this: does atom radiate at all? And this was the chorus from the crowd. Naturally, it is bound to happen, because anyone knows some fundamentals of science. Of course, light coming out of the atom and spectra is of course there, and this you are going in reverse rather by telling what? You're telling that you propose non-radiating paths. Naturally this question arises, does the atom radiate at all? And then was a forceful man. It's not easy. People are intimidating him and stop the lecture because you cannot propose non-radiating paths. But remember that Niels Bohr has done his homework. And in spite of great rebellion, he sticks to this, and he tries to intimidate the crowd by underlining this. Yes, of course, I propose what? The non-radiating paths. No going back on that. And he was telling the crowd that I will explain how atom is radiating. I will explain this question, but please sit down. Let me answer this. And I'll come to that, how the light is coming out from the atom. But I stick to what I'm telling, and I propose what? Non-radiating paths for electrons without any doubt. And is actually intimidating the crowd rather by underlining again that I propose non-radiating paths. So in spite of people intimidating him And he wanted to ask this question. He's not running away. Because this you need to answer, because does atom radiate at all? After all, the immediate question that comes out, because you're actually proposing non-radiating paths, so naturally the question will come out, does atom radiate at all or not? Of course it radiates, and Bohr is telling that yes, I'll come to that, but I think I'll stick to what I'm telling, and I propose non-radiating paths, and let's draw inferences from what is non-radiating path is. Now remember, NRPs synonymously are basically called stationary orbits. Stationary orbits. You must understand. Or otherwise, I call this to be simply an orbit, I call this to be a shell. And this NRP is what I'm actually referring to Mumbai when I was actually telling you that, you know, when you wanted to write a letter to your friend in Mumbai, it's a larger area, that's Mumbai. So I'm actually getting into to find out where the electron is, to pinpoint the address of the electron. I'm not at least pinpointing it, I'm actually telling you that it is, of course, there in the shell. Right? So these NRPs are also called stationary orbits. They say, why do we call this? Please understand, when you say it's a non-radiating path, the electron is neither emitting energy nor vomiting energy. So the total energy of the electron in that particular orbit remains constant. When you say, I'm not losing 1 rupee from my pocket, nor gaining 1 rupee from my pocket, that means that the 1 rupee in my pocket remains constant. That's what your suggestion is, simply. So when you propose non-radiating paths, then the energy of the electron remains constant as long as the orbit, as long as it is in the orbit. You must understand that, right? Here, I wanted to have a much better matured thinking for the students. Normally, the perception is, you know, in the textbooks, it is basically drawn. Here is the nucleus, here is a shell, here is an electron, as if there are permanent roads as we see outside, and there are permanent paths around the nucleus. Absolutely not. I draw the attention. Please understand, have a matured thinking that electron itself is a shell. Electron itself is a shell. And I convincingly say this because when there is no electron, no shell. It's not like the paths or roads which are there outside, where in the night time when the vehicles doesn't go or you don't walk, the roads don't disappear in the next day morning. So I have a thinking, and you must be also inducing the thinking, that electron and the path, electron or the shell, electron or the non-radiating path, electron or the subshell, electron or the orbital, whatever, these are all electrons. Mind you that there are no permanent paths, you know, that has rolled over the nucleus, where, you know, in spite of no electrons also the paths remain. It's absolutely wrong. Remove that thinking from your mind and remove all this which is drawn in your earlier classes for your understanding. Remember, no electron, no shell. So synonymously, electrons are shells, electrons are orbits, electrons are NRPs, electrons are non-radiating paths. Electrons are orbitals, electrons are subshells. You don't distinguish these, right? If one is not there, the other don't exist. No electrons, no shells. Mind you that, right? That perception must be induced into you. So, in spite of some rebellion, does atom radiate at all? He is telling that I stick to non-radiating paths. Here are the stationary orbits. NRPs are also called stationary orbits for the simple reason because as long as the electron is in the orbit, you are neither radiating energy nor what? Emitting energy. That means the energy's orbit remains constant. Hence, I call this to be stationary orbit. And sometimes, yes, you can call this to be an orbit. Sometimes you call this to be a shell. So, shell, orbit, stationary orbit, NRPs are basically first proposed by Bohr. You must understand, these are the wordings that are proposed by Bohr, and this synonymously I call this to be Mumbai, as I was actually telling you initially, to pinpoint the address of your friend. You must understand this, right? So if any time you dial Bohr and ask him where exactly is the atom in his life, he has only shell, only orbit, only non-radiating path, only stationary orbit. All these four are synonymous. Except this, in Bohr, he has nothing to offer to you. Except Mumbai, he has nothing to offer to you. You must understand. If you ask him where is the electron, it is there in the shell. That's all. Except shell, it doesn't know anything. Now the question is, you know, people are not trivial. People are not trivial. They will ask you questions. Now, when you said stationary orbit, non-radiating path, you're basically telling that the electron's orbit, the electron's energy remains constant. You just cannot claim that the electron's energy is remaining constant and run away. Because they will ask you how much. They will ask you how much. And how do you calculate it? You require an equation. You just cannot say the orbit is non-radiating. So when it's non-radiating, the electron's energy must be constant because you're neither emitting energy nor absorbing energy. So if you say that the energy of the electron is constant, people will question you. People will ask you, how do you calculate and how much is this? Right? So it's time to get into equations. Before I get into the equations, look into this, what I'm telling. His proposal is he's proposing non-radiating paths for electrons around the nucleus, right? Around the nucleus in an atom. Now, when you propose non-radiating paths, the energy of the orbit in the path, as long as the electron is in the orbit, it's neither emitting energy nor losing energy. So we need to calculate, right, how much is the energy that is constant, because when you're not losing 1 rupee from your pocket, nor gaining 1 rupee from the pocket, I think the 1 rupee remains constant. And how much is that constant? People are asking you. And remember, there is pending one question. There is pending one question because you propose non-radiating paths. People have already asked you, does atom radiate at all? And he has actually said that I'll be doing that little later. And now it's time to check out how much is the energy and how do we calculate. Watch here carefully now. Watch. Look here. When you propose such a thing, when you propose the proposal, NRPs for electrons. When you propose non-radiating paths for electrons, then the electron's energy. Now when I say electron's energy, synonymously it's shell energy. Synonymously it is orbit. Synonymously it is what? The shell. You must understand. So NRPs for electrons, that means electron's energy is basically constant. You just cannot claim that the energy is constant and run away. You cannot do that. You need to stay and tell them how do you calculate that and how much is that. Because after all, let me also remind you, an atom has infinite number of shells. How many shells does an atom have? Infinite. So 1, 2, 3, 4, 5, 6, like that you have infinite. Now each orbit's or each shell's energy must be calculated because you have actually proposed non-radiating paths. That means that each shell's energy remains constant as long as the electron is in the infinite number of shells. It must be what? Constant. And how do you calculate that? Is I give you a volley of equations. You must understand. Here is a volley of equations, right? Look here. So since you proposed NRPs for electrons, electrons' energy is constant and calculated by the formulae. And look into the formulas I quote. Watch carefully here. And here is the first formula. En is equal to minus 13.6 by n square electron volts. You must understand. Minus 13.6 by n square electron volts. You must understand this. Right? Now, what do you mean by this? For example, if someone is asking you, you said that the electron is in the first orbit. You said that the electron is in the first orbit. When in the first orbit, the electron is neither emitting energy nor losing energy. So, how much is the energy? That is constant. So, if you wanted to calculate, then it is E1, which is equal to minus 13.6 by 1 square electron volts. You must understand. So, it is minus 13.6 electron volts is the energy of the first orbit's electron. So, the electron is in the first orbit, the total energy remains constant, that is 13.6 electron volts. Now, people who are watching this, what is this bloody minus sign over here? What is this bloody minus sign over here? And what do you mean by electron volts? You must answer this, right? Now, what is this minus sign? First of all, understand that this minus sign has physical significance. Now, what is the physical significance is, let me explain this. You know, there was an electron somewhere at infinity. Somewhere at infinity it is there. Let's say God, right? The electron is at the infinity. Someone has done some work. They are doing some work in bringing the electron from infinity, and they brought till the nucleus is catching that electron. Till the nucleus is catching that electron. That means you're bringing the electron from infinity to the influence of the nucleus such that the atom is constructed. Who constructed? That is a separate issue. But I think it's a common sense which is telling you that the electron is brought from infinity to a particular point, and the point is now the nucleus is having the influence on the electron and it's catching it. Right? Now it's a common sense when you're pursuing science that when someone is bringing it from infinity to a point, naturally energy is lost. And that's nothing but the potential energy which you have used it, lost. That's what is called the minus sign, you must understand. So someone has brought the electron from infinity to the first orbit. The energy is lost. How much is energy lost? It is 13.6. Why minus? Because it is lost. So the minus has physical significance. You must understand this. You must understand this. So, you know why all this is cropping up first? Why all this is cropping up first? Because you fellow have proposed non-radiating paths. When you propose non-radiating paths, people will ask you, how much is the electron's energy in the orbit? Right? Then you must be giving a formula, acute formula rather, a small formulae that is nothing but minus 13.6 by n square. That is even. Now suppose if you wanted to find E2, then that is equal to minus 13.6 by 2 square. Right? That will be equal to minus 3.4 electron volts. Right? And then suppose if you want to find E3, that is minus 13.6 by 3 square, that is minus 1.5 electron volts, you must understand. This minus sign will not leave you because you are bringing the electron from the infinity, placing them to the first orbit, second orbit, third orbit, and thereby you have spent some energy. Now the common sense says that if anyone wanted to remove the electron from the shell, from that particular orbit, they need to spend same amount of energy, but that will be plus. So minus is warning people that I have spent some energy to bringing the electron from infinity to a particular point, and if you wanted to remove that, you need to spend an equal amount of energy such that it can be extricated. That's what is told. Now that's the physical significance of the minus sign. Now coming to what is electron volt. Now understand what is electron volt is. What is electron volt? The fundamentals are important. What is electron volt? What is electron volt is, you must understand, many people don't know, so I would like to define what exactly is electron volt. Right? Now, understand one point that, the force, I would like to quote, the force experienced. The force experienced. Someone is actually pushing you. When someone pushes you, you experience the force. Experience means you're not dancing at the same point, you're not dancing at the same point. Please understand that. So someone is pushing you, you're experiencing the force, then you actually move. That means you actually move. You're not experiencing the force remaining at the same point. So I would like to say the force experienced by an electron in moving through a potential difference of 1 volt. You must understand. So actually the fundamentals are, when you wanted to move a charged particle, you need to have a potential difference. Just like that it doesn't. You need to do some work. Right? If the potential difference is 1 volt, right, then the force experienced by the electron in moving through a potential of 1 volt can be called, this is what is called 1 electron volt. You must understand. That is how the definition is, the electron volt. Now force experience. Now what do you mean by force experience? Force experience is someone is pushing you. You're not standing at the same point and experiencing the force. It's not like that. You are actually moving it. So otherwise, synonymously, I would like to call this, right, the kinetic energy of electron, because actually it's a mechanical motion. Someone is pushing you. Right? Someone is pushing you. So the kinetic energy of electron in actually moving through a potential of 1 volt is also called electron volt. You must understand this, right? So why all this discussion is cropping up? Let me check it out, because you fellow is basically proposing non-radiating path. When you propose non-radiating path, the electron's energy in the orbit will remain constant. Right? It will remain constant. You must understand this. Right? And then when it remains constant, the natural question arises, how do you actually measure that? Right? How do you measure that? I give you a formula which is En is equal to minus 13.6 by n square electron volts, minus indicating that I have done some work in bringing the electron from infinity and brought it to the first orbit, second orbit, third orbit. And then, as I told you, the atom has infinite number of orbits. It's up to you. to calculate energy of the orbit, because I proposed non-radiating path, man. So I have given you an equation, E1, E2, E3, E4, E5, E6, whatever, right? Whatever, you must understand that, you can calculate the energy of any orbit. It's up to you, right? And what is an electron volt? It's nothing but the force experienced by an electron in moving through a potential difference of 1 volt, or otherwise the kinetic energy of the electron in moving through a potential of 1 volt. You must understand this. So when you are actually proposing non-radiating paths, the obvious question was how to calculate energy, and here is the energy equation. En is minus 13.6 by n square electron volts. And what is electron volt? I have told you the force experienced by an electron in moving through a potential difference of 1 volt. Because any charged particle, if you wanted to move from one point to the other, you require a potential difference. That's nothing but the work need to be done in moving a unit positive charge or negative charge from a point to the other point. So naturally you need to do work. That's how the potential is defined. So the force experienced is nothing but the kinetic energy of the electron. So simply I can say that the kinetic energy is nothing but an electron volt. You must understand this, right? I have other ways of expressing this non-radiating paths also. Watch carefully. I put all the equations at one place. Watch carefully here. Right. So what are the energy equations? Now NRP, or I call this to be stationary orbit. And what are the energy equations? En is minus 13.6 by n square electron volts. N can be varying from 1 to infinity rather, right? Or En is equal to minus 2.178 into 10 power minus 11 ergs by n square. Ergs is also an energy unit, you must understand, right? Or otherwise, En is equal to minus 2.179 into 10 power minus 18 joules by n square. And if you wanted to have a relation between these three, I think you equate this with this and you have a relation between the ergs and the electron volts. And suppose if you wanted to have a relation between electron volt and joules, equate these two and then you will find a relation between joules and electron volts. But I have written the energy equations in all what? In all the units possible, right? So remember, so it is you have actually told all this because you proposed non-radiating paths and the electron in the path is neither emitting energy nor losing energy, and we have infinite number of shells or paths around the nucleus. Then if you wanted to calculate the energy, which is basically constant for an electron, then I think you can use this equation and this equation. You must understand. But here is one more point, right? Because when you actually wanted to propose something, you need to designate that. So what I will do here, the main point, the main proposal, in fact, NRP, I would like to quote something here. Proposal of NRP. Proposal of NRP by Bohr actually fetched him Nobel Prize. This single statement of the proposal of non-radiating path fetched him Nobel Prize. Because it is this which will explain the stability of the atom. No one has actually done that before, right? So when you propose NRPs, as I said, these NRPs are designated by a number. Because you need to tell, you have to designate, you have to name, you have to give an identity. Because we have an identity. If you call by my name, Chandrasekhar, then I say I raise my hand because I have my own identity. Similarly, if you wanted to say that the electron is in the shell, because in Bohr's theory, or in the life of Bohr, except shell there is nothing, except orbit there is nothing, except non-radiating path there is absolutely nothing. You need to give an identity. As I said, shell is Mumbai. Mumbai has a pin code. Similarly, I can simply say that the NRBs are designated by a number, and this is called basically principal quantum number n. You must understand. So similarly, it's because you ask anything about, anything with regard to the structure of atom to Bohr. He has only one thing. If you ask where is the electron in the atom, Bohr has only one thing to say, except shell. He doesn't know anything, right? Hence you have drawbacks of Bohr also. But remember that, here as you have the Mumbai having a pin code, similarly, principal quantum number is actually giving the identity to the shell. You must understand this. So if I say n value starts from 1, 2, 3, and as I told you, you have infinite number of what? Orbits, right? Infinite number of orbits, and it doesn't start from 0 because that's ruled out because the electron is outside the nucleus. If you give 0, the electron is in the nucleus, then I think you cannot explain the stability of the atom. Of course, there are other things to explain. So principal quantum number n is equal to 1, 2, 3 up to infinity, and n is equal to 1 is the first orbit, right? First orbit, and 2 is the second orbit, 3 is the third orbit. So whenever you wanted to dial Bohr, and ask him where is the electron, he will simply say NRP or shell or orbital or the principal quantum number. So if you know, we should be smartly answering when someone is asking us questions. If you ask me, well, I would like to write rather what I will do if someone is asking me. If someone is asking me, right, if someone has asked this question to me, you know, this question to me, what is the greatest merit of Bohr? What is the greatest merit of Bohr, right? If someone is asking me, then I don't tell all the story. What I will do is, I just say introduction of principal quantum number, that's PQN, principal quantum number, itself is a merit. Itself is a merit designated by n. Introduction of the principal quantum number itself is a merit. Why it's a merit? Because this PQN is nothing but your NRP. This PQN itself is a shell. This PQN itself is an orbit. This PQN is sometimes even called stationary orbit. The introduction of this itself is a merit of Bohr, and all these are designated by a quantum number. That's nothing but the principal quantum number. You must understand this, right? Now, if this is the case, then people are waiting. And people are waiting for you, right? What are they waiting for? Because you propose non-radiating path and you say that the electrons are neither emitting energy nor losing energy. Now it's time to tell us where does the light come out from the atom, because you promised that you asked her to sit down such that you can explain that in postulate number 2. Where does the light come out? It's time for that explanation. Let us do that. Now the question prevails. You have silenced people. You have silenced people and you proposed NRPs, right? Now the question is, when you actually propose NRPs, non-radiating paths for electrons, right? Then the obvious question that arises, right, is does atom radiate at all? Because you propose non-radiating paths, then people will ask you, does atom radiate at all? Yes, you need to answer that, because earlier you told that, I'll be explaining that in postulate number 2. So how do you explain this? The reality is you don't need to ask a question. Rather, everyone know. Everyone know. Even, the light comes out from the atom. Of course, it comes out from the atom. Now, the only thing is you need to explain. Why you need to explain? Because you proposed non-radiating path. When you propose non-radiating path, then naturally you need to explain this. So how do you explain? So I go for postulate number 2. Postulate 2. Now in postulate 2, what are you doing? What are you going to explain? This fellow will explain spectra. That is, that he will explain to you light coming out from the atom. Light coming out from the atom, because electrons around the nucleus are not radiating. That's what you told in the first postulate. In the second postulate, you need to explain spectra and how does atom radiate, if at all it radiates, right? So what he's telling basically here, postulate 2, he says that, look into this, look into this. Look at this, he's so proud of himself. He says, I, my, he used singulars. He's so confident. And watch here, what he's telling, transitions. It is basically transitions. Transitions are jumps, right? Transitions between my, look into how confident he is. Look into how confident he is. He is just proposing it. He didn't receive the Nobel Prize. It's a proposal. He's trying to convince the crowd. What is he trying to convince? If the atom is radiating. And if atom is radiating, then you already proposed non-radiating path, it will not vomit energy. So for that, he's giving explanation. He's basically telling the transition between my NRPs. Transitions between my NRPs is the reason for spectra. Is the reasons for spectra. Now when I say spectra, the light that comes out of atom. You must understand this. It is not, I draw the attention. Now, electron in the orbit when it's revolving, it's neither emitting energy nor vomiting energy. And I stick to it. For that proposal of NRP, which revolutionized science, I received Nobel Prize. There is no going back till date, till time. That remains. NRP is, of course, the one which prevails now. Now the question arises, if you propose NRP, how does the light come out? And that is explained in postulate number 2. And look at this, what he is saying. Transitions between my NRPs is the reason for spectra. That is for the light that comes out of an atom. That's the reason for spectra. Not while the electron is revolving around the nucleus. Well, let us explain this. Look into this diagram here. Here is the nucleus. Here is the first orbit. Here is the second orbit. Right? And if I calculate the energy of this NRP, then it is minus 13.6 electron volts. That is the energy of the orbit which he was proposing in the first step. Second is E2, that is minus 3.5 electron volts, right? This is the electron which is moving in the first orbit. This is the electron which is moving in the second orbit. Assume, now remember, this energy is 13.6 and 3.6 will remain constant as long as the electron is in the orbit. As long as the electron is revolving in this orbit, I think this energy will remain constant. Similarly, as the electron is revolving in the second orbit, the 3.5 electron volts energy shall remain constant. Now, obvious question is, where is the light coming out? Then if that is the case, where is the light coming out from? That's what he's telling. He is telling transitions between my NRPs is the reason for the light. Now, what is the intelligent factor here is, watch carefully, the electron is revolving in the second orbit. It got bored. Bloody, it's revolving only in the second orbit. It's boring, man. So it wanted to come out to the first orbit. So, at the electron in the second orbit wanted to revolve in the first orbit, and it wanted to come down to the first orbit because you got bored in the second orbit. You can't bring all your energy and mix it in my pocket of what? 3.5. Already I'm 13.6, the energy of the first orbit. And if you bring your energy also, that is minus 3.5 and 13.6, and if you add it to me, then the first postulate goes wrong. Because the energy of the orbit remains constant. You cannot bring all the energy of the second orbit and add it to the first orbit. If that is the case, if you add it, just because you got bored in the second orbit, and you wanted to bring the 3.5 also and add it to the 13.6, it's not possible. Because I propose non-radiating path. The energy of the orbit is constant. So what to do? Because this remains constant, that remains constant, and you wanted to come here. When you wanted to come here, you can't mix your energy with my energy. So what to do is the issue. Now what we will do is, the only option left for you is, when you wanted to jump from the second orbit to the first orbit, and if you wanted to jump, you need to vomit this. Vomit the energy. You need to vomit it out. You cannot bring all your energy and mix it to me, because energy of each orbit is constant. So what it is doing, it is vomiting it, and this is the vomit quantity. That's the vomit quantity. How much you need to vomit? E2 minus E1. So what is E2 minus E1? Minus 3.5 minus 13.6 is plus 10.2 electrons, plus approximately 10 electron volts is the vomit. So if an electron in the second orbit vomits 10.2 electron volts energy, then you are supposed to actually come and then revolve in the first orbit. Otherwise, you cannot bring all your energy, mix it onto me, such that, you know, the energy of the orbit, which was supposed to be constant, will vary. Then the entire Bohr's theory is a collapse, and it's similar to Rutherford's theory. So if an electron in the higher energy wanted to come to the lower energy, then you need to vomit that excess energy. You need to vomit that excess energy and then come and revolve in the first orbit or the lower orbits. You must understand. Now this vomited energy comes out of atom. Comes out of atom, and that is what is seen as a spectra. That's what is seen as a spectra. So understand that electron in the orbit revolving, it's not vomiting energy, because the energy of the orbit remains constant. It is only when you jump from higher orbits to lower orbits, the excess energy which is vomited out is coming out from the atom, and that is how he was able to explain the spectra. You must understand this. So it is transitions between his NRPs is the reason for the spectra, and not electron while revolving in the orbit is actually what giving out the energy. You must understand this. We will go into the postulate number 3 in the next class. For serious students who wanted to pursue engineering and medicine and who wanted to write their exams, immediate exams, this is a serious channel you must be subscribing to and follow regularly. You need not run here and there. Just follow T1 channel and Tone channel, and we'll be lecturing and we'll be helping you out in this endeavor. Thank you.